All right, team. Tragically, we only have 2 more lectures. I'm so sorry. Let's see if we can hang on emotionally and get through it. All right, so we are going to talk about one last topic. And you've been prepared for this with lots of matrix foo training. Singular value decomposition. I'll give you some examples where this is used in the last lecture. Show you some fun things. But we're going to work through the mechanics of this, and everything is set up. All the stuff about eigenvalues and eigenvectors that you know about, symmetric matrices, all that goodness will come together. And this will be for matrices, arbitrary matrices. So we've had some of these examples where, so this is for rectangles, matrices of unusual size. In general, this will be an m by n in here. We'll get to it. And an m by n in here, and an m by m. This will complete that whole big picture story as well. All right. YouTube is 10 years old, so well done, YouTube. All right. It's pretty weird. It's only 10. Okay, so we're going to, this will just kind of come out for free. It's a pretty, lots of monks, again, died for this, but that was their choice. And I'll give you the nice little path that's left with the bodies on the side. All right. Okay, what else? Oh yeah, well, we better look at the website. All right, so this is what we're going to get to. So we've seen this big picture. So these pieces in red are the new part, right? So the basis stories that we had, we got a basis for row space and null space. We had a method for doing this. Now we'll get the spectacular, natural, beautiful bases out for them. So we're going to get orthogonal. They must be orthogonal, right? Because that's the best kind of basis. That'll come out for free because matrices are awesome. All right. And it will be a bit like the eigenvalue equation. You can dispute that, I guess. It'll be a bit like the eigenvalue equation, but a twist on it. Okay, so your last assignment is here. It's Tetris. Tetris, 1984. Okay, so that is undroppable. This one counts. Everything you need. So it does have the positive definite matrix stuff in it. It's online. But there's 6 questions in a row. They're all around one SVD problem. Okay, let me see if I can bring this up. My PhD, I kind of escaped from the math department and ended up in the Earth Sciences building, which is called the Green Building at MIT. All the buildings have numbers because they hate humans, right? So every course, everything is called a number. But so math is just called 18. No one says math. This is building 50. But actually, people did call this Green Building. It's a horrible building. It's in the middle. It's got a ball on top. Anyway, so hacking, the word hacking comes from MIT, actually, right? That people would, the idea was but it's a prank. It's not a bad thing. It was a prank, right? So you would hack, they would commit a hack on someone else. Like they'd blow up a balloon in the middle of a Yale, Harvard, I forgot about it. A Yale-Harvard game that says MIT rules or something. Yeah, right. And I think they train birds. I think it's true. There's a museum for hacks. They went through bird seed out in the middle of a field every day at a certain time for 6 months, and then all these pigeons descended in the middle of a game. All those sorts of things, right? One time, actually, it was the start of the horrendous prequels for Star Wars. I was going for a run, and I looked back over the Charles, and the main dome had been turned into R2-D2, which was quite nice. Okay, so this is the building I was in. Let me get it to run. And I don't think we need sound for this. So it's a big, tall building, and they put little LED lights in each window, the big slabs of window, and turned it into Tetris, which you can play from a distance. So you sit back, 100 yards from the thing and play Tetris on a building. And it's sort of the holy grail of hacks at MIT, and they managed to do it. Now, some people opt out. I don't know if you can see very well. There you go. It's coming down. That's one of the little. Are they going to get a thing? No, they're in trouble. So. Anyway, that was pretty great. So, and then they put up all sorts of things, ribbons and things. Let's get it when it crashes. This is bad Tetris playing. There you go. It goes down. Game over. Tetris. This is, pretty good. There was a rule that any hack that you make, you have to be able to clean it up, right? No one gets hurt. It has to be cleaned up. Everything has to be removed. That's the rule. This one, they actually glued the thing in, and you can opt out. There's a switch if you're, if you're in one of those rooms, you just say no, which is a bit sad. But if you look on the little computer chip, because my advisor's in the top floor of this still, so it says, MIT Tetris hack. Pretty great. All right, so you can look at that. This is me patting a cat talking about singular value decomposition. Do you want to listen to that? This is our neighbor's cat. This cat is ridiculous. We don't own this cat. This cat owns us. It comes along, as cats do, to just dominate you. Will this work? I'm not sure if this will work.
It's terrible, isn't it? Because you have to roll around. You're so tired. So tired.
Can you hear that?
It's hard being a cat. It's hard being a cat. Really?
Can you hear anything?
Those green eyes. Yeah? You like singular value decomposition? Oh, you love the singular value decomposition. Yes. Oh, yes, it's so great. Yeah, A times A transpose. Suddenly it's a rectangular matrix becomes a square matrix. And it's symmetric, so it's very magical. Yeah, isn't it great? Yeah, and it works for every matrix. You get your orthogonal eigenvectors, you get positive eigenvalues, you get your S3. What's going on? What's going on? This is the best. I know, I'm so excited. You're terrible.
All right. Right. The usual story with cats, right? They do all this business, but they're plotting to kill you while this is all going along. How will I murder this person? Anyway. Okay. So we'll have some of that silliness going on. What else can we tell you? Okay, so the levels are up. We've got this one. There are grade distributions for, which one is this? Oh, Pitfall. Yeah, that's up. I'll give you 3 things back, I think, on Tuesday. It's going to be the 3rd exam and assignments 8 and 9. Right, levels 8 and 9. Okay, and Tetris is due not next Tuesday, right? We're going to have a lecture on it still, so it's going to be due on the Thursday, and you can come to Farrell Hall to drop that off. There'll be tweets about it, information. I think we're kind of there. Grade distributions are up. Yep, I said that. What else? Okay, that's good. That's good. All right. Okay, let's do this SVD thing. So we're set up for this. This is pretty great. This is going to work for all. So we good? I'll get rid of this. This is going to work for any matrix. Big deal. Pick mute and up. All right, team, the exciting denouement to the course. All right. Okay, so singular value decomposition. Just awful branding, right? This just says do not touch. Like this is. Nothing is fun about this, but it is awesome. And this is what we're going to do. All right, so we did all this stuff with diagonalization. It's very beautiful, right? But it fails in a couple of ways. So we kind of like that. If we could diagonalize all matrices, that would be awesome. It gives us all sorts of good things. So let's monk observations, all right? We desire things. So diagonalization is great. And we'd love to, and we'd like to do this for all matrices. We'd like it to work, something like this to work for all matrices. It's great. Work for all matrices. And it's even better with symmetric matrices. Amazing with symmetric matrices. All right, so this is an observation. So it fails in several ways to be extensible. Several ways. So one is, kind of the big one is it's only for n by n, only for square matrices. So we've been kind of living in square matrix world, but that's okay. It's all going to be good. We have to have, so types of A, I'll just kind of write it like that. A must have, this will all come out so nicely. Must have no pivots. Pivots are kind of out of this, all right? Just the joy of eigenvalues. Must have n linearly independent E vectors, which was absolutely true for symmetric matrices, right? So that was, yep. Always true for A equals A transpose. So that was kind of a big deal. So we'll use that fact again. in a little bit. It's a tragic little t. Okay. Okay. That's just a little note. And even if we do have them, the E-vector basis, these are problems. So the E-vector basis may not be orthogonal, right? And again, it's this point of symmetry that may not be orthogonal. Okay. Yes. So let's do that. So these are bad things. So we're going to overcome this. We'll get it sort of a factorization. So this is what we're going to get to. It's a factorization of all A. That helps us in lots of ways, and I'll show you some things. It helps us with things like data compression, finding the most important aspects of a matrix, right? Being able to say this matrix is this bit plus this bit plus this bit plus this bit, and this bit, these guys are small and zero. We can kind of get rid of them, right? So there's a sense of saying here are the main pieces of something. And you can use this in all sorts of ways, right? All right, so, and it will complete our big picture. So let me say that. Okay, so, all right, so here's the idea. So we had this, so let's see. So we've got the eigenstory. We're going to build from that. Yes, this is great. The eigenstory, which you are thrilled with, right, is A times V equals lambda times V. Brilliant. It's terrific. We know this is where we get our diagonalization from. So what's going on here? It's simple. We have the same vector here. So this is, and V is also has to be an element of Rn, and this is n by n. So these are the sort of characteristics. So we have to give this up, right? We have to give this up if we move to, right? So we give this up in moving to Rn. In moving to n by n, which sends vectors from Rn to Rm, if you like. Right? We can't do it anymore. We can't have A times a vector is something times that vector because they're in a different, if it's not a square matrix, they're in just simply in a different space. So we have to loosen that up. But we really like orthogonality. So we'll give this up, but we'll go for orthogonality. Orthogonality, right? So orthogonality. So that was not, orthogonality was not guaranteed for eigenvectors. Was not guaranteed. But we want this. We want a guarantee on this. All right, excitement, I know. So our big picture is going to start to look like this. You remember this, I know it's been a little while, so we've got this thing. So the idea will be we'll have vectors in here, and this is going to be kind of a crude looking thing. These ones are over here, let me get them right. So these ones will be, this will be V, we'll still call it V, that's V1. This will be VR, and this will be, say, V, I in the middle here, that's a V. These will be U's, U1, there'll be a U I in the middle, and a UR. We'll fill this in, it's okay. The idea is, this is an orthogonal basis, so these are all actually at right angles. We can't see it because it's high dimensional. So these are supposed to be at right angles. And the idea is we'll get this map, A times, let me get it right, VI will equal sigma I, so this is a new thing, sigma I times UI. Let me write that in different color. So this is going to be A times V I equals sigma I UI. So it looks a bit like an eigenvector equation. The U's live over here in column space in Rm. So this is Rm, and this is Rn. So the V's are over here, V's are over here, and the U's are over here. So the V's form an orthogonal basis for Rn, and the U's will form an orthogonal basis for, an orthonormal basis, I should say, for Rm. Callum. These ones? Yeah. So this is 1, the number 1. And this is an I. And this is R, where R is rank. It is rank. We'll get to it. I'll draw it again, but there'll be more down here. There's going to be V R plus 1 all the way across to Vn. So it's a full set. Some of them describe null space. Let me just write that. This is null space of A, and I'll come to your question. This is row space, which we know is the column space of A transpose, column space, and null space of A transpose. Yeah, I'll write it out. Let me write it out again here. So we'll come back to this. So, but here's the new glorious equation. All right, so it's going to be this. So the new story, a new hope. All right, will be this: A times Vi equals sigma I Ui. This is sigma, right? And big sigma, right? It's Greek for S. Does that go? Yes, yeah. So right. So let's write these things. So let's write some details here. So we'll have Vi is perpendicular to Vj. So I'll write some notes here for you. I not equal to j. Right. We're going to get this. So these are the goodies. I not equal to j, and these are hats. They have little hats because they're little party characters. And we have this one. This is not I not equal to j. They're orthogonal to each other. The v's form a basis, form an orthonormal basis. Orthonormal basis for Rn. So I'm kind of making all these claims right now, and then we'll get to it. And then the U's do the same thing, but for Rn. M for monkey, right. So before we got out bases for these different spaces, but they were just somewhat a little ramshackle. They weren't great. So, and the sigma is a number. Sigma you can think of kind of, it's a generalization or inspired by eigenvalues. Right? Eigenvalues were just numbers. The sigma I are the singular values. So these are elements of the real numbers. Are the singular, actually, let me say this is an important thing. The sigma I are greater than or equal to 0 are the singular values of A. The very special values. Eigen meant self, so it had something to do with the selfness of it, and these are the special values. So this is going to be another guarantee that they're all greater than or equal to 0, which helps us because negatives can be confusing, right? So this is also a guarantee. So we want all these things. We really like orthogonality. That makes it very simple to understand things. So we really want this, and it'd be nice if we can connect the bases across, right? A times any basis vector that's in the null space goes to 0. So that's fine. But it's really about connecting this subspace to this subspace. It's R-dimensional here, R-dimensional here. And we'll get to an example. I'm going to derive things, and then we'll work through an example. All right, let's do it. Good, good, good. How are we doing? More questions? Good questions. Always good questions. Good team. Okay. Okay, so yeah, so how we now see A times X. Like this. We're going to write it like this. A is going to B, and we're going to derive and show that this is possible, again, because of monks who have been slain. Okay, there's going to be U, sigma, V transpose. And what we have to remember is change of bases. Okay, so let's explain what these things are then. So this is, it's in general an m by n, and so sigma is kind of A, right? Sigma is A, just like capital lambda was A. It's the guts of it. So this is n by n, and this is m by m. And so so let's do it like this. So V equals these guys. We're going to stack them. V1, let me write like that. V1, V2, we're going to stack these things across to Vn. So this thing acts as a change of basis. Basis matrix. Right? And because it's orthogonal, V to the minus 1 equals V transpose. And so V transpose sends a vector in the natural basis to V's basis. In the natural basis, right, our I hat, J hat, K hat, to a representation in V basis. It doesn't do anything to it. It doesn't rotate it or stretch it in V basis. So there's this. So sigma does the work. Sigma takes the VI to sigma I times UI. So this does the work of A. The work of A, right? And so now it's a bit simpler. The rotation is in the U's and the V's, right? It's like where they end up is an issue. But this is just a number that's greater than or equal to 0. So it can only sort of stretch it. It doesn't flip anything. No funny business there. All right. I know these are all words, but we'll get to it. And you can come back to this and read this. So, and then the U, which will equal this, I guess I should show. Let me write what sigma is. Sigma is going to look like this. Sigma, I'm going to put little things there, is, and it's going to have sigma 1, sigma 2, sigma 3, all the way down to sigma r. And then, in principle, everything else is 0, all zeros, down to 0. And this will be, it's m by n. So there are n here. And m this way. Everything's 0 except for these numbers on the diagonal. And, important thing, and we order them by significance. So sigma 1 is greater than or equal to sigma 2, is greater than or equal to sigma 3, greater than or equal down to sigma r, and then sigma r plus 1 equals 0, etc. The rest is 0. When you go beyond the rank, there's nothing. All right, so we're just lots of monks. This is just what happened. All right, so we have this and we have U. That's going to be just a stack of these guys as well. U2. Let's get it done. And this is going to be UM. So this is an M by M. Oh, it's my mistake. It's confusing. Oh well. This guy, so what this, again, this is a transformation of basis. So think of transforms from U basis back to natural basis. So you can go back and look at, so it's the same idea as this. Same idea as A equals S lambda S to the minus 1. This takes it into the eigenvector basis. This does the work. This brings it back to the natural basis. This takes you into the V basis. Sigma does the work, takes you back into natural basis. Yep. Yeah, so where's my thing here? Yeah. So the layout is like this. This is an m by n, it's a rectangle. So maybe let me draw a little, so I can get this right. So here's a little illustration. So this will be, A. Maybe it's let's say one that's wide. This will be sigma. So these guys look the same. They have the same shape. Then we have squares around them. This is a smaller square for U. And then this is a bigger square for V transpose. All right? So this is the deep story. The sigma is really representing what A does. This stuff encoded in the U's and V's. Yeah.
Are the B's still the eigenvectors?
They are eigenvectors of something. They are eigenvectors of something. And sigmas are eigenvalues of something. Well, not quite the sigmas. All right. So let's... Because we know about symmetric matrices, we can do this. All right. So I think I've laid things out. So the goal is to find all these things, right? So I'm claiming this is all going to work. So we need to sort of just show that mechanically this is all possible. Okay, so that's the setup. So small calculations will be able to do it, which is amazing. All right. Information loss fear. Okay, all right. You too. All right, let's go. Okay, so let's do some trickery. And then we'll work through an example, all right? So I'm going to do this, and then we're going to work through an example. That is the way it is. All right, this is out of the way. I think I've told you all these things. Yeah, so important thing is the sigmas will be ordered. We get to choose that. So this one is the most important one. Most important. You actually not allowed to use the word significant much in science because it's been destroyed by statisticians. Well, scientists who then use it in a bad way. All right, so let's see. So we want this to be true. So the goal for this thing now, is to show that this is true. All right, so claim is all of this is possible, right? So let's see if we can do this. Well, I'm going to just sort of stating that this is the structure that we can make for every A, that U will be a basis for column space and left null space, an orthogonal one, orthonormal one. V inside it will have an orthonormal basis for row space and null space, and sigma will be just this nice diagonal thing. And that every A can do this. All right, so outrageous claim. Outrageous claim. So let's use everything we've done to get there. All right, so now working around, so it says another great moment in linear algebra, all right? Monks say, consider, they whisper to you, A transpose A. Let's look at A transpose A. We've talked about this thing. So what's special about A transpose A? Or any A. So this is m by n. In general, this thing is going to be n by m. So the whole thing is n by, yep. So it's n by n. So this is a square matrix, always square. What else about it? There's a charming feature of this. I take any A, take A transpose, multiply it by A, and I get a matrix that is square, and it has one other feature about it. What? It may or may not be. This is right, symmetric. Aha. So A transpose A, huge deal. A transpose A is always symmetric. Always symmetric. Square, symmetric. Let's use our sneaky thing. So we have A transpose A. We just take the transpose of it. And we want to see if it's the same thing. A transpose A. Well, we use the result that AB transpose equals B transpose A. Transpose. So the first one comes to the front, and that's A transpose. The second one goes to the back, and it's A transpose transpose. So it's A transpose A. So the transpose of this blob is itself symmetric. All right, so that's good. Now, we're claiming we can do this. So let's bung all of this in and see what happens. See what we get. OK, so this is a good thing to know. It's symmetric. So, all right, so it's symmetric. Therefore, it has what? Symmetric matrices are excellent matrices. They always produce. You can diagonalize them, and they have a full set of eigenvectors that form an orthogonal basis for Rn. So we are, right, so here's our big deal. So we know we'll get an orthogonal, well, I'll say orthonormal. You can always make it orthonormal basis from E vectors of A. Transpose A. Huge. So this is great, right? Boom. OK, so let's do that. So shove A equals U sigma V transpose in. And see what happens. So let's do it. So we're going to put it in. So A transpose A. Someone's dead, I guess. A transpose A equals U sigma V transpose. That's A, right? Transpose. Let's make it a little clearer, maybe. Boom. And then let's stick this one in here. So we're going to have U sigma V transpose. Right? So here's A transpose. Here's A. So see right down the next line. Trying to get someone to hide under here. So high-fiving is quite mandatory soon. This one, what happens to that? Right? We're basically, it's generalization of this. They go backwards and get transposes, right? OK, so the first one, so this is going to be equal to V transpose with a transpose, and then sigma transpose, and then U transpose. And then we have, so that's the first blob. This is still all of A transpose. And then the second blob is U sigma V transpose. We see a joyous thing. What do we see? What's good in here? We're requiring something about U, so. OK, right, so let's get them. So this one here, U transpose equals the inverse of U. That's because we want these things to be orthonormal, right? The vectors in U, these guys, they're all at right angles to each other. Here. They're all at right angles to each other. So U, the inverse of U is U transpose. So this blob here is just the identity. So that goes whoop, away. And so and this is V transpose transpose, so we end up with V. And we have to think a little bit about this one. So what's this? It's sigma transpose sigma, and then V transpose. So let's get our dimensions correct. We've stipulated certain things. This is an m by n. This is an n by n. This one looks like A, so it's m by n, and then we have the transpose. So it's n by m. So the whole thing here is n by n. So square matrix, square matrix, square matrix. Let's write down what we have here. So this is going to be V, and the thing in the middle is going to have this kind of structure. Sigma 1 squared, sigma 2 squared, sigma 3 squared, and we've said that it only goes down to sigma r squared, and then 0, down to 0, all of these are zeros, all of these are zeros. And then this will be V transpose. And this is an m by n, this is an m by n, and this is an m by n. It's diagonal. Square. So this looks like what? It looks like it is diagonalization, right? So we've got diagonalization. So we're back to, so this is what we've been writing as. This whole thing is saying that we have A transpose A equals, it looks like this. I'll write as Q lambda Q transpose. It's diagonalization. Yes. So we know we can do this. We believe in this. The fact that there are zeros here, we'll get to that. But we believe this. These are all positive too. We kind of want that to be positive. So we'll see if that comes out. All right. So we can do this. We know this works. The excitement, the palpable excitement. All right, we know this works. So, although there's a couple of things, so the sigma I squared equals E values of A transpose A. The V holds the E vectors of A transpose A. So we have to say we're not sure that these are positive yet. No, we're not sure yet that that lambdas of A transpose A are greater than or equal to 0. So that's a little bit of a worry, right? But we spent a couple of lectures on figuring out that is going to be true. Okay, so we have A transpose A. It's got an orthonormal. It produces an orthonormal basis for Rn, so that's good. Let's think a little bit about these eigenvalues. There's something special, again, because it's A transpose A. So I'm going to call this section, this is joy. This is joy. This is joy augmentation. So we get one. This is like the free set of tofu knives situation, right? Or steak, you can do whatever you want. So joy augmentation, we have, where are the things? Okay, look at this. Aha, monks say try this. They suggest this. Let's try this. X transpose A transpose A times X. So we're going to fiddle around with this thing. We'll just do it, and I'll talk about it. So what's going on here? I can rearrange this a little bit. There is a something transpose. We love that stuff. That's AX transpose, and then multiplying AX. Right? This whole thing, this is a m by n, m by 1. We're going to scoop up a result here, m by n, m by 1. The whole thing is an m by 1. Right? This looks like it's an inner product. This is a number. This is an inner product, right? A dot product. And and in fact, it's this, right? It's actually the length of this thing squared because it's a vector transpose times multiplying itself, right? Blob transpose blob. So it is the length of AX, whatever that is, squared. What is a very nice thing we know about numbers that are squared? They are positive, right? And in fact, they're always at least 0, right? So we're allowed to say that. This setup here, this is the whole setup for positive definite matrices. We worked through this. This is the positive, and in this case, it's the semi-positive definite matrix setup. Right? We worked to this. We showed that, right? So, and I'll just, let me write B. So if B is so recall, I know you like remembering things, recall semi-positive, I'll write it out without the silly little things, positive definite, then X transpose B times X, it's m by n, this is m by n. This is greater than or equal to 0 for all x. And this corresponds with the E values of B are greater than or equal to 0. Those are the two things we joined together. We also had a thing about the pivots. We're going to leave the pivots. Pivots can go away. And this is the statement. We've just showed that it's positive definite, right? This A transpose A, doesn't matter what A is, this, you have to go back and remember this construction. If we take any x, so this is for any x, this thing is semi-positive definite, which we showed means that its eigenvalues are always greater than or equal to 0. So A transpose A's E values are greater than or equal to 0, which means that this whole thing of saying this is going to be true. We're going to have positive, 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 maybe some zeros. It's always true. And you can sort them by, you can sort eigenvalues by their size. So the sigma I squared greater than or equal to 0 works. So it works. So it's absolutely true. So we got these things. So for A transpose A, messing around with it, and we claim that A can be written as this U sigma V transpose. We will get out that that's fine. We can have positive numbers in here. So the sigma i's will be the square root of the E values of A transpose A. Crazy. This is crazy. Okay. This is hurtful. Let's do the other one. So what about, and I know what about A transpose? And why would we think about that? There's a reason for that, A transpose. So what happens if we do A transpose? We're just going to stick, what? The transpose is going to be over here. So what happens to that one? So A transpose equals, let's just put it all in. We have, I got to get this right. So U sigma V, and then U sigma, and there's a transpose there. U sigma V transpose. So the transpose happens over here now. We flip that one and transpose everything. So this is still going to be U, and there'll be a sigma here, and then V transpose, that's all of this. This one comes over here, V transpose is just V. Sigma transpose is here, and then this is U transpose. Same story. This is the identity. Orthogonal matrices. The inverse of V is right here. So we end up with U, and we end up with a slightly different thing. This is sigma transpose times U transpose. This is not, in general, what is this? This is an M by M. This is an M by M. This whole thing, because it's M by N and then N by M, is an M by M. So this guy is going to look like sigma 1 squared, sigma 2 squared, down to sigma r squared again, and then zeros, but it's going to be M by M, which may or may not. So it's only the same as, where's that other blob? It's only the same as sigma transpose sigma if M is equal to N. Otherwise, they're different sizes. Little detail. But you can see the whole story is going to pop out again. This is, again, a diagonalization story. right? So the U's, the things that are in U, are the eigenvectors of AA transpose. And the sigmas, this is kind of a crazy thing, that eigenvalues of AA transpose must match up, at least for the non-zero things. Let me write that somewhere. Okay, I'll run the next board. I know, and then we're going to work on an example, which we must speed on towards. Speeding. How are we doing with that? Basically, we smashed it around until we saw that, in fact, we get diagonalization again, which we know all about. But we did have to use this positive definite story, which again works for AA transpose. I'm not going to show you that here. Okay. Wow, that's great. Totally great. So, same idea, same as for A transpose A, kind of same idea. We get this. We get AA transposes E values equal the sigma I squareds, and AA transposes E vectors, because it's symmetric, form the orthonormal basis, the U's, right? These guys. So A transpose A gives us the V's, AA transpose gives us the U's. So we're going to do one more little painful step. And then we'll do some calculations. I kind of wanted to make a joke, but all right, I've got to be careful. There's one last thing. We haven't shown this, right? We have not really shown this. We've shown that we will get an isoorthonormal basis, and it will be connected to A transpose A. The V's will come from that. The U's will come from AA transpose, and both of them will give us these sigmas. And they'll definitely, it's okay to have sigma squared. That's cool. Super cool. All right. Last piece to show. And then we'll get to an example because I know it's hurting. It's beginning to hurt. That show is that indeed we get A times V hat I equals sigma I ui. So there's going to be some sneakiness for this. Right? A times the right? So these ones come from, this is weird. These come from A transpose A, E vectors. And this one comes from A transposes, E vectors. And this is, these characters in here are E values. We know they're E values of both, which is kind of nuts, A transpose A and A transpose. They're different sizes, right? So this is n by n, and this is m by m. So they will have matching eigenvalues up to some zero. There'll be some zero eigenvalues, right? One might be longer than the other. Let's do it. Let's do it. Okay. So let's prove that. So again, just small calculations. Monks died for this, but they're small calculations. Okay. It can be done very deftly. So we need two things. Let me show you. So two pieces. And you'll have to look at this one. So one is that we'll show the length. Let me see. Where are we? Right? These are unit lengths. Unit lengths. So the length of this thing, this whole thing is sigma I. Okay? So show the length of A times VI is sigma I. So that's got to match up. It's got to have that length, right? A times this is some vector, and we know that it must have this length. This is unit length. So let's do that. Again, sneaky, sneaky things. So we know we have A transpose A times VI, this, is equal to sigma I squared times VI, right? From before, this is true, right? This is a matrix. That's its eigenvector. This is an eigenvalue equation, right? This is an eigenvalue equation, right? Matrix, square matrix times a vector equals a number times a vector. We know this is true. And it's positive definite, so we know that this could be written as something squared, semi-positive definite. So we take this, in the usual business, we think of a sneaky little thing. So we're going to take VI transpose times, so we're going to pre-multiply by this, VI. And over here, we're going to get sigma I squared as a number, and then VI transpose VI. Maybe I should write a different color. Let's write a different color. So this is, we're bringing this one in, VI transpose, and this is VI transpose. All right, so what happens over here? What's VI transpose times VI, the unit vectors? 1? 1, right? It's I and I, so this is just 1. 1. This one, we do our sneaky, dirty tricks again. We're going to rewrite this as A VI transpose. See that? If we undo that, it'd be VI transpose, A transpose, using the transpose rule. It's crazy how these things... Right? So this is equal to sigma I squared now. What is this thing? This is a vector transpose times that same vector. So it is its length squared. It's the length of A V I squared equals sigma I squared. So therefore, the length of A V I, this vector, is sigma I. So that's, we needed that. This is a funny little calculation, but it all works out. What I should say is it's fine once you get going, right? Once the monks say, try that, or you try a million things yourself, and you say, oh, I'm going to do that, right? I mean, you can be okay, all right, too much. So we know, but we also need to know that it points in the direction of UI. So we know the length is okay. So part 2 is, we need to show that A times VI, actually it's really this, let me write it like this, I get points in the same direction, I'll write it like that, I guess, same direction as the UI, right? It really is that vector. A times VI points in that direction. We know it's got the right length, which is, another way to say this is it's an eigenvector. So eigenvector. So it's going to be this, A transpose, I can do this. All right, so we know, again, we know this. We know that A transpose, no, I'm sorry about this. Yes, this is right. So we know this, again. So we know this, A transpose A times VI, same thing again, equals sigma I squared times VI. This is, again, our eigenvalue equation. Let's do something. So before we pre-multiply by this VI transpose, because we're trying to just get to a length, here we're trying to show it's an eigenvector, actually. So we're going to pre-multiply both sides by A and A over here. This is sneaky. Sneaky. Times VI. And then all of this is here, A transpose A times VI hat. So, little rearrangement here. This is one piece, A transpose, blob. And then this is one piece, A. And you will need to look at it later on, I guess. But this is this. And then we have sigma I squared times A V I hat. So let's stare at this a little bit in dismay. What is this equation? What's the shape of AA transpose? Square, and it's m by m. Okay, this is m by m. This is n by n times an n by 1. So this is n by 1. And there's the same thing. N by 1, so these are the same. Matrix times a vector equals a number times that vector. This is an eigenvalue equation. And it's an eigenvalue equation for AA transpose. So, and we know that the way we wrote it is that this must be some multiple of, well, we know what it is. This must be, at this point, plus or minus sigma I times ui. So we know the length. We know the length of this. This is a unit vector. And ui is explicitly, right, because A transpose times ui, this is our second piece, is equal to sigma I squared times ui hat. So this blob must be this blob, or some multiple of this blob. It's a multiple of this blob, right? We can dial the eigenvectors up and down. But this matches, this structure matches. It's all there. So you're going to have to take a deep breath and look through these again. But all of this shows that this whole crazy business here works. We can do this. We can always find them, and there's a good way to find them. All right. Okay. An example. I don't think I have the... I was going to be silly, but I don't think I will. All right. All right. Okay. So let's start on this calculation. Okay? Exciting. We've got all the theory. We're all set up. We know this is true. Now we can do it. And you basically just use this story over again, right? You find A transpose A, find the eigenvectors and the eigenvalues associated with it. The eigenvectors for A transpose A are the V's. The eigenvalues are the square of the singular values. And then you need to find the U's. And then once you've got it all together, you can stick it all into one big piece. All right. Okay. So we've done this. Okay. An example. So we're going to do this one. A equals a fifth. This funny looking thing here. And you'll have a 2 by 3 to work on in your problem set, which makes it a little bit more interesting. Okay. So the claim is it's going to look like this. It's going to look like V1 hat. It's a 2 by 2. V2 hat. It's a 2 by 2. There'll be some singular values in here. And then there'll be, over here, there'll be U1. No, these are U's. U's. Sorry, U. And the V's are here. This will be V1 hat transpose. Yes, V1 hat, V2 hat transpose. All right, we're losing steam. V transpose sigma. It's 2 by 2, so we don't quite get all the shape things. But in general, this is m by m. This is the m by n. And this is the m by n. Okay. So we're just going to simply use this, what we use for this proof of all of these things, over. So let's see if we can do it. Okay, so first step. Find the V's and this is in general, and the sigma I squareds from A transpose A. So there's the first job. Compute A transpose A. Let's do that. There'll be one little trick we'll have to put in there. A transpose A equals a fifth. Take the transpose. Put the 11 here, 10, 2, 5, 1/5, 2, 10, 11, 5. Whoop. It's just A. No. I want A transpose. I've done it. And then I want A over here. Yep. 10, 5. It's going to be a 25th. And then some stuff in here. Let's race. Let's see if we can do it. All right. I'll take photos. You calculate that. There you go. Okay. Huh. Good. Alrighty, let's do it. Okay, so we have to do a little eigenvalue stuff, all right? It's going to look a little horrible, so let's do it in a sneaky way. Ah. Okay. So you should have A transpose A should look something like 2/25. I'm going to pull a 2 out of it, factor it out because it's good, and 52, 36, 73. All-time excellent random number, okay? And this is symmetric as is guaranteed. A transpose A must be symmetric. So if you compute A transpose or A transpose A symmetric, and you don't get a symmetric matrix, you are in trouble. Check. So find the eigenvalues and eigenvectors of this thing. It's a little nasty. So here's a sneaky trick. Sneaky trick number 37. Let's say we have B times lambda equals lambda times V, right? So it's an eigenvalue equation. B times V equals lambda times V. And then we look at this version. We didn't really V this one. C times, we just multiply C. We multiply this whole thing. C times lambda V. So if V is an eigenvector of B with eigenvalue lambda, then it's also an eigenvector of CB. So V is an E vector of CB, right? Some constant times B but it has a modified eigenvalue. It's a simple one. It's just multiplied by that with E value C lambda. And the reason we want to do that is because this is a bit of a nasty little beast out here. So we could just ignore that. We'll find the eigenvalues for this and then multiply them by 2/25. Okay, so find E values of this thing, 52, 36, 73. So off we go, right? So we're going to do the whole thing. So it's A minus lambda I equals 52, it's a determinant, 52 minus lambda, 73 minus lambda, minus 36 squared. And this has to be all equal to 0. It seems odd, but this thing will actually work out nicely. Okay, so let's do this. Good. I think we'll at least get as far as finding the V's and the sigmas. Okay, there's a 36 squared there. Good. Okay, yeah. Good. So we can compute these things. So we'll get lambda squared. I can do this in my head, but so there'll be, right, we get this cross term here, so it's 73 plus 52, so it's minus 125 times lambda. And then we have 73 times 52. So what is that, 3,500, we're going to end up with 37, it's going to be a plus 3796. And then minus 36 squared. 1,296, so that's going to work out. So we want all of this, and there'll be lambda, minus 125 lambda. This thing subtracts off nicely, which is amazing. Of course it will. We trust. There's a lambda squared lambda here. Right. Factor this thing. It's going to be something something here. What do you think? You do that funny little thing, don't you? What's that? Okay, good. 25 and 100, negatives. Good. minus 125. Excellent. Good. So we got lambda equals 25 and 100. So this would be lambda, and we'll do it like this. This would be lambda 1, we want the big one now, and then lambda 2 would be 25. Greater than or equal to 0. Greater than or equal to 0. Guaranteed, right? But we have to multiply by 2/25 to get the right number. So sigma, so multiply by 2/25 using our sneaky rule, we'll get sigma 1 squared equals, what's 2 times 25 of 100? 8. And 2 times 25 of this is 2. Sigma 2 squared equals 2. Great. All right. What a funny thing to do. OK, so we've got this. We're pretty close. Now we have to find the e-vectors. And these will be v1 and v2. So it's, again, it's going to be A transpose A, this kind of stuff, minus lambda I times vi equals 0. You guys have done these things. So there's an I in there. Identity matrix. Got it. OK, let's do this one. All right, so time. So there's going to be 2 over 25, 52, 36, 36. Oh, yeah, let me show you the thing. So, and then it'll be minus the first one. So the first one is, there's a 2 over 25 times 100. So let's do that. 2 over 25 times 100 times the identity, 1, 0, 0, 1. All of this times v, 1. We'll get v1, yep. So the 225s can come out. Right, we can get rid of those. So it's useful to keep them floating around. What do we get? 100 off of this. So the 100 is going to be subtracted from this. So it's 48. Minus 48. 36. 36. And then 100 from this one. Minus 27. So this is our problem, 0, 0. Right? We're solving a little null space problem. This is a little note about 2x2s. When you do an eigenvector problem with 2x2s, the second row, the rows have to be multiples of each other, right? Because we've got a solution here. If this was not a multiple of this one, then we end up with 1 and 1 here, and we'd end up with 0 as being the only solution. Okay. So 3/4 of this one, 3/4 of this one. That's true. So second row, always a multiple. That's a bit of a hint of first row in for 2x2s. Can't do it for others. So what do we end up with? And then you can also just swap them. It's very nice. You just swap the things, right? So this is really kind of -4 to 3. So we can just write down v1 equals, and I'll put it here, 3. So we'll swap them and change the sign. It's -4 and 3, right? That's the balance. Just swap. So I'm going to put a 3 up to here. It was a -4 goes down here, and a 3 goes up here. And we'll just swap the sign. Whoop. And that will work, right? So 3 times this plus 4 times this gives you 0. So what's the length of this thing? What's the length of a 3, 4 vector? Because we want to make it a unit vector. 5. 3 squared plus 4 squared is 25. So it's one of those good ones. So somehow in this horrible thing, this was here, if you go through and find v2, you'll find the same thing. Same kind of thing. So solve for v2. For v2, insert your work, right? Which you're excited about doing later on, I suppose. We would end up with, yeah, v2 hat equals, should I choose this one? Yeah, a fifth, -4, and 3. So same kind of thing, the 4 and the 3 are in there again, so we get the nice normalization. These things are, they're orthogonal. right? As guaranteed. Lots of guarantees. V1 is hat is orthogonal to V2, right? It was a symmetric matrix, real symmetric matrix. It was definitely going to happen. So far we have this. We have A equals, and it's just, A is an odd thing. A was a fifth, 2, 10, 11, and 5. So far we have this. It's equal to, I'm going to put the fifth out the front. No, we don't. So it's U. We don't know what U is. And then we have the sigmas. So the sigmas are 8 and 2. So it's the square root of 8. And the square root of 2. So this is sigma 2, sigma 1. And we have, over here, we'll have V transpose. So it's going to be a fifth. And the first one is 3, 4. 3, 4. And then the next one is minus 4, 3. Minus 4, 3. Right? So this is V2 transpose and V1 transpose. So we could solve AA transpose U. Right? We could do all this, and we'll get this one out. We should do that too. But we could solve this, right, to find these other eigenvectors. But much easier. Better plan is this, and everything should work out. Because we're guaranteed this, is we just use this fact: A times V I equals sigma I times UI. And so we can just divide through by the sigmas. This is at least for the ones that are where there's a real sigma. Okay, times A VI equals UI. Right, so just compute A times the eigenvectors that we ended up with and divide them by, sigma I. So let's do one of those. We'll have more fun next time. We'll do one of those. So it's going to be, this is the wrong page. Let's do one of them. Yeah, A times V1. We're going to finish. A times V1 will be a fifth, 2, 11, 10, 5, times a fifth, 3 quarters, 3, 4. So let's multiply through. So we get 6 plus 44 is 50. Divided by 5 is 2. Right? 10 times 3 is 30. Plus 5 times 4 is 50. Divided by 5 gives us another 2. That's A times VI. So let's divide it by the first singular value. 1 over the square root of 8. That was the square root of 8 times 2. So the square root of 8, right? That's 4 times 2 in there. So this is 2 root 2. The 2's cancel. So this is 1 over root 2, 1, 1. Which is, what kind of vector is that? That is unit vector, which we expected. So it worked, must be a unit vector. So everything cleans up. Amazing, hashtag amazing, right? So that's, we're guaranteed to do it, but it's kind of bananas. So that's a unit vector. And then the last one would be A times V2. Let's do it. It's 1/5, 2, 11, 10, 5, and we have slight difference. We have 1, 5, minus 4, 3. This is fun to calculate. 2, so it's minus 8 plus 33, 25. Divide that by 25, we get 1. Then minus 40 plus 15 is minus 25. Divide that by 25, we get 1. We get minus 1. And so we divide this all by 1 over root 2. This is sigma 2. 1 over root 2. 1 over root 2. So this is U2 hat. This is U1 hat. And it works, right? So we have 1 minus 1. This is a unit vector. It's at right angles to this one. So this is This is a basis for, this is a fine basis for 2 dimensions. So let's go back to here and we'll put it in. So this is going to be 1 over root 2, 1, 1, and the next one was 1 minus 1. So unbelievably, this is a very useful way to look at A. It's not as nice as, in some ways, as the eigenvalue one, right? Potentially. There's going to be some messy things here. We're going to definitely have square roots for normalization. U, sigma, V transpose. All right, there's going to be more of this on Tuesday. But you can start on Tetris. You can get onto it. All right.